Alright, here's the video reviewing the first three questions of our practice. We start with question 1, determining limits. And part A, B, and C all are the same rational function, a rational function being a fraction, in other words, with a polynomial in the numerator and a polynomial in the denominator. And so the first thing that we want to do is to factor the numerator and see if there is a factor that is common to both numerator and denominator that we can cancel out. And we see, in fact, that yes, there is. So you just have to do this factorization once and you come up with x plus 2. And then you take the limit, different limits, 0, 3, and negative 2, for each of you take each of those limits for the same reduced function. And so since this rational function equals x plus 2, we take the limit as x approaches 0, and so we just substitute 0 in for x, and 0 plus 2 is 2, so that's your first limit. Now as x approaches 3, we again take the limit of the same reduced function, x plus 2, which means we just substitute a 3 in for the x, and so that's 3 plus 2 is equal to 5. So that's that limit. Now you'll notice, perhaps, that in the denominator here, 3 minus 3 is 0, and we can't divide by 0. That means that there would be a hole in the graph of this function, but the limit still exists, and it is, in fact, 5. And finally, we take the limit as x approaches negative 2. And so once again, we plug the negative 2 in for x here. And so negative 2 plus 2 is 0. So that's the third of these limits, the limit of that reduced function in part C. Now, in question 2, we will be using the formal definition of continuity at a point to determine whether this particular rational function is continuous at x equals 3. And we need to do a few things to do this. We need to first evaluate the function at this value of x, 3. So that means that wherever we've got an x, we put a set of parentheses. Wherever we've got an x, we put a set of parentheses, and inside those parentheses we place the argument that's found here. Remember, the argument is whatever is being whatever is inside these parentheses. So we substitute a 3 in here, 3 for x. 3 squared is 9, 9 minus 9 is 0, and as long as the denominator is not 0, then 0 divided by, and we see that the denominator is 6, 0 divided by 6 is 0. Then, after we've evaluated the function at 3, we need to take the limit as x approaches that value, 3. And just as we did in question 1, we need to reduce this function if possible. And so, yes, it is possible. X squared minus 9 is the difference of two squares, and so it factors like so. The factor x minus 3 times the factor x plus 3, and we see that x plus 3 is common to both numerator and denominator, and so we cancel them out and substitute the 3 in for x, and 3 minus 3 is 0. So, since the value of the function is at 3 is 0, and the limit as x approaches 3 of that function is 0, then, and this means therefore, or we can conclude, or then, f of x is continuous at x equals 3. When we have the function value equal to the limit at the value in question, which in this case is 3, then we have continuity. Now the third question asks us to use the definition of the derivative to show that the derivative of square root of x is equal to 1 over 2 times the square root of x. And so the definition of the derivative, as you recall, is the limit as h approaches 0 of f of x plus h minus f of x over h. Well, since the function is the square root of x, then the function evaluated at x plus h just means that we substitute x plus h in. X plus h is the argument, and simplify from there. Well, there's not a lot we can do to break that x plus h out of there, but the one thing that we can do is multiply by the conjugate. The conjugate. So we have this term minus this term. Its conjugate is this term plus this term. And when we do that, we again get the difference of two squares, so that means that we square this, so that's x plus h, and we square this, so that's x. Difference of two squares, just like up here. And then in the denominator, we're multiplying h times all of these terms. Now, we're not expanding this here. There's no need to multiply this out, because when we cancel additively, the x's up here, x minus x is 0, and that leaves h in the numerator. Then we see that we have the common factor of h in the numerator and denominator, which cancel out, which leaves 1 over the denominator we got from multiplying this conjugate, square root of x plus h plus the square root of x. Then we are able to substitute 0 in for h here. X plus 0 is x, so this is 1 over square root of x plus square root of x, which means that there's 2 square roots of x, and so we get our final result, 1 over 2 times the square root of x.